What I'm here to talk to you about today is streaming and where we are going in Zio for our vision of streams. Streams are something that is very important to computing in general, computing in Scala, and where we want to go with Zio. So we've put a lot of thought into this, and we want to share with you where that's gotten us so far, kind of where we are and where we're going. So I'm going to proceed in 4 parts today. First, I just want to talk about what are streams. I feel like anytime we talk about something, it's useful to take a little bit of time and just really say, what is this thing that we're talking about, and not assume that we know what it is we're talking about. Because often when we step back from our assumptions, we find we learn more than if we just walk blindly forward with something. Then I want to look at some of the ways we've represented streams historically. Streams are very rich, so you can represent them a bunch of different ways. And even if you look at what we've done in Zio over the life of Zio, we've represented them several different ways with several different trade-offs, and we'll see what we can learn from that. And then what we'll try to take from there is this alternative idea of streams as being fundamental. And I'll try to unpack for you what that means. And once we build up from that, that will let us take the next step and say, OK, where are we going from here? So first question, what are streams? You try to answer this question a couple different ways. So one thing you can just say is, they're those things in those libraries, right? We know what AccaStream is. We know what ZioStream is. It's that data type in those libraries, which, OK, that's a factually accurate statement, but maybe not the most insightful about what the underlying essence of this thing is. We might go a level deeper. We might say they're collection-like types that perform input and output. And I think that definitely captures a lot of the intuitions we have when we work with streams, that it's this collection-like thing, and we can filter it, or we can map it, or we can take a certain number of elements for it. But it's not just this thing that is there. It's this thing that is maybe reading from Twitter or writing somewhere. But again, it feels like maybe that's not the fundamental essence of the thing. We've got kind of the elephant, and we're like feeling the elephant's trunk, but we're not reaching the essential description of what this thing is. And so what I'm going to propose is that the essential definition of a stream is it's a computation that produces its result incrementally. And we can unpack that a little bit more by comparing streams with Zio, or with any of these effect types that you've probably heard a lot about today, right? This morning we heard from Adam Worski about all these different effect and quasi-effect types. And if you look at all of them, they're actually all the same in this way. We'll focus on Zio, but the things I say are going to apply to any of those data types. And so if we look at Zio, it has this type signature of this Zio REA that we talk about. And the contract of that is that this is some workflow that, if it completes successfully at all, is going to complete with exactly one value of type A. And otherwise, it's going to fail with an E, or it's never going to complete. But it's going to do one of those things. And so a Zio is fundamentally binary, that it's either in a stage of it's not done yet, it's processing, and then it basically has no information for you. Maybe there's a fiber, maybe you can get its ID, but it has no other information for you. Or it's done, and it has all the information that it's ever going to have for you, and it's never going to do anything else. So you can think of it as your kind of difficult coworker who you ask them to do some project, and they say, OK, I'm going to go away and do it. And they start working on it, but when you ask them the week from now how it's going, they say, leave me alone. I'll come back to you when it's done, but don't bother me until it's done, which is not always the most helpful thing, but that's what they do. Now, you might say, well, hold on a sec. Couldn't we have workflows that do work incrementally? So like here, I've got this relatively simple Zio workflow that is just going to write random integers to this queue every second. And it's going to do that forever. So we could say, OK, this workflow does work incrementally, right? Every second, there's a new integer being put in this queue. And that's true. But what we said was the definition is, do they produce their results incrementally? And if we look at this workflow, yes, it does work incrementally, but it actually doesn't produce any results, incrementally or otherwise, because its return type here is essentially any, right? We don't have, yes, it's offering these things to this queue, but we don't have the ability to map and transform those values. We don't have the ability to take a certain number of those values. We don't have the ability to do anything with that because that incremental work is reflected in essentially a side channel here. It's not reflected in the return type of this data type. And so there's nothing we can do with it to process it further in a compositional way. So streams are the opposite of that. So when we look at a stream, and here we're going to look at the Z-stream data type, but again, this is going to apply to any streaming data type we want to talk about. The contract here is that this stream is going to produce 0 or more and potentially infinitely many values of type A. And possibly some of those values are going to be available now, and some of those values are not even going to be available now, but are going to be available in the future, right? If we have a stream of tweets about Taylor Swift, our stream may have some tweets that exist today and some that haven't even been written yet, that are going to be written 5 minutes from now or written an hour from now. And so again, that's fundamentally different than if we have like a Zio that returns a chunk of A values. We might think both of these feel similar because both of them are returning multiple values, but there's actually a big difference here of this Zio RE chunk of A is binary, right? It has either nothing at all or it has the entire chunk that it's ever going to produce. Versus this stream is incremental. It may have some values now, it may have more values in the future. And this, I think, gives the explanation of why streaming is so important. That it's not just kind of a arbitrary thing of, well, there are a bunch of businesses that care about this, so we need to have something for them. It's actually reflecting something about the nature of reality. That change in our world occurs incrementally. And that can be true at a very small scale, right? If we read a file, we don't just read the entire file. That's not the way that the lowest level of computers works. We read a set of bytes, and then we read some more bytes, and then we read some more bytes. And the way we read a file is we just read a set of bytes, and we just keep doing that until we've read all the bytes. And that also applies at a much larger scale. So if we think about the business logic concerns, or even just more broadly our concerns, change occurs incrementally, right? If we're a company and we're trying to estimate the likelihood that there's fraud, we don't just go from knowing nothing to knowing everything. We get incremental pieces of data, right? Adam made a purchase in London. Well, that's unusual, but well, Adam sometimes goes to London, so fair enough. Adam bought an iPhone in London. Well, that's a little bit unusual, but Adam sometimes buys iPhones. Adam buys 10 iPhones in London. OK, now this is getting a little bit suspicious here, right? Each of those gives us incremental information. And the same thing is true if we think about financial markets. What was the stock market going to do? Every day we get new information about, are we going into a recession? Are we not going into a recession? Every day we get new information about how world events are going. So this idea of incremental information, incremental change, and reacting to that and processing that is actually very fundamental, and I think explains why streaming is such an important paradigm. OK, so now that we understand what streams are, let's talk about some of the different ways that we've represented them in Zio. And I'm not going to say this is a comprehensive way of all the ways that streams can be represented, because they're rich enough they can be represented many different ways. But I think we'll see, just in looking at different ways, that we in this particular software library have represented them in these different ways, some of the variations and some of the advantages and disadvantages of each. So over the life of Zio, I think there have been three main ways we've represented streams. So there's a pre-Zio 1.0 encoding of streams as things that can be folded over. Then there's what I call the encoding of streams as effectual iterators. And then there's the Zio 2.0 encoding of streams as channels. So let's look at each of these in a little more detail. So the first way that we represented streams in Zio is this concept of just a stream is something that you can fold to produce a summary value. And so we have this somewhat scary looking type signature. But actually, if you look at this a little bit, you can say this is really just a fold left or a lazy fold left, right? This is saying a stream is something that you can fold. You give it this starting summary value. You give it a function that's going to take that summary value and going to take one of the elements to produce a new summary value. Except here it's going to do some kind of effect. And here it's going to be able to be resourceful, because we're in the Zio 1.0 world right now, so this was Z managed. And then it just has this one other parameter, this continue function, that lets you say, do you want to continue the fold? So you don't have to fold the whole stream, because the whole stream is maybe infinite. And so this was the initial implementation of streams prior to Zio 1.0. And in a way, it had some logic to it, right? Of it builds on this analogy of streams as collections. Of if you think about collections, one of the most fundamental operators you could have on a collection is being able to fold it and reduce it to a summary value. And so if you say, okay, well, it's a collection-like thing, but it does I/O, so you can't just fold it to produce a value. You have to fold it in the context of some effect or some workflow. Okay, fair enough. And then you can implement all these different stream operators by just transforming these folds. So you implement a new stream that maps the original stream or filters it or does something else by defining a new fold in terms of the old fold. And that actually let you support a very rich interface. One of the interesting things about this is, as we'll see, some of these representations are very different, but they essentially all supported the same very rich API that was essentially the same API that you can get from other streaming libraries, you can get from Akka streams. So there are a lot of different ways to approach the same thing and support the same ultimate behavior for end users. So that had some issues. Some of them were around stack safety. There were some other issues. So prior to the release of Zio 1.0, we moved to this definition of streams as effectual iterators. And I think this was actually, in a way, one of the nicest implementations in terms of at least being the most teachable. Because the way to think about this is that this outer Z managed thing that you have here corresponds to creating an iterator, right? So if you call .iterator on a collection, you're creating a stateful thing. And if we want to be in this purely functional world, that needs to be wrapped up in an effect constructor, because you're creating this stateful thing. To be referentially transparent, it needs to be in one of these constructors. And then what it gives you inside, this Zio that either gives you an A or fails with an option of E, you can think of every time you evaluate that, you're calling iterator.next. And so it's either giving you an A, or it's telling you, I'm done. And the way it tells you it's done is it fails with a none. And then we have the possibility there's going to be some actual error that we're going to throw some exception when we try to read from this socket or what have you. And so we also have the E to handle that error type. And so I think this was actually a really nice description in a way, because it was just very, very intuitive, I think, of once you kind of got that idea of this is like an iterator. I think to some of the earlier discussions today, like the one that Alex did, we make fun of some things in Java, but some things in Java exist and have existed for a long time because they actually end up being pretty powerful to describe things and sometimes pretty intuitive. And so this idea of it being this iterator was a very flexible, very powerful, of basically any kind of custom operator you wanted, you could define of like, I want to take these two streams and combine them, and I want to pull two things from here, and then I want to pull three things from here, and then I want to pull another one from here. And you could do that. So it was very flexible. If anything, it was maybe too flexible because it let you just implement all of these different one-off operators, and it didn't force you to do it in a way where they were based on a small number of primitives that had very well-defined behavior. So OK, we've looked at these two different ways of representing streams. What can we synthesize about some of the advantages and disadvantages of each of them? So first, as I mentioned, both of these, even though being fairly different if you just look at the representation, supported this very rich range of stream operators, where essentially we went from one to the other. The API did not shrink at all in terms of the operators that you could call on streams as we moved from one to the other. You could support the same very broad set of operations with each of them. Another advantage, at least we felt like it was an advantage at the time, was that you were able to leverage Zio for a lot of the hard stuff of asynchronous and concurrent programming. So you want to race getting values from two different streams as part of merging them. Well, you just pull from each of them and you race those pulls. And that race is the Zio race that we've already implemented and that has all these tests and all this optimization behind it. And you get to leverage all that stuff. So that's great. And as I mentioned before, this idea of this effectual iterator was a very powerful analogy that made it very easy to implement custom stream operators, maybe, if anything, too easy. So what are some of the disadvantages of that? Well, I think one of the biggest ones was I wasn't actually being fully honest with you when I showed the signature of that effectual iterator a couple slides ago. And in particular, what I didn't show there was this chunk here. So the issue with both of these representations of either the fold or the iterator is that every time you took a step in doing the fold, or every time that you did a pull on the iterator, you went through a Zio workflow. And Zio tries to be very efficient, tries to be very low overhead. But the reality is if you're doing very low-level stream operations, and every one of these things is like a byte or a small number of bytes, like that overhead of every one of those things being a Zio workflow adds up. And so what this led to is this idea of chunking. And so you'll see here that this signature became, when you pulled on this iterator, you didn't just get a single A, you got a chunk of A's. So in the iterator world, you can imagine this isn't just an iterator of A's, it's an iterator of chunks of A's. And every time you pull on it, you eventually are going to get some chunk that maybe is going to have one element, maybe it's going to have 4,000 elements. And this helps you address this performance issue because you amortize the costs of the effect system over each of those pulls. So now instead of pulling once for every element, maybe I'm pulling once for every 4,096 elements. So OK, helps there. But that ended up, I think, being an imperfect abstraction, you could say, where as long as you maintain those chunks, that really helped you out. But you could run into operators that, for reasons of correctness, were not able to maintain the chunk structure. And then you could have situations where you saw a large performance difference because you did some operator that didn't preserve chunking there. So then going to Zio 2.0, we implemented this idea of streams as channels. And so we created this Z channel data type, which has more type parameters than you can shake a stick at, has 7 of them in all. But what it let us do is define a stream in terms of a channel. And that had a couple of advantages. So one is that you were able to represent streams, sinks, and pipelines, kind of all the different parts of a streaming library as this one data type. And the other thing that you could do there is, instead of representing these channels directly in terms of ZIO, now this channel is its own data type that got executed by this thing called a channel executor. And so this channel executor let you bypass the ZIO runtime for operations that were purely synchronous and didn't involve ZIO workflows. So if all I'm doing is some data processing of I'm taking a bunch of elements and I'm adding to them and I'm filtering them and I'm doing mathy operations like that, that whole thing can take place in this channel executor, and I never have to go to ZIO at all. Except maybe at the very end, I just wrap the whole thing in a ZIO so that I keep everything in the same world. And as we talked about, this let me unify streams and sinks and pipelines. So that was great. And we still leverage ZIO for this hard stuff of the asynchronous and concurrent programming. Anytime we wanted to do a asynchronous or concurrent operation, we would just call the appropriate ZIO operator. We would wrap that up. We would delegate to the ZIO runtime, and then we would put that back into a channel. But this thing, again, had some disadvantages. So I think one of the biggest ones was it could be very easy to fall out of that happy path. So I just said, hey, if all of our operations are synchronous and we're not doing any ZIO workflows, then we get to operate in this world where we're just processing in this channel executor. But in your real streams, how often does that happen? You probably want to do some type of merging different streams, right? Merging streams is a concurrent operator. You want to, let's say you just want to tap the stream, right? You just want to do like a tap and you want to like log the elements. Well, all of those, that's a ZIO workflow, right? So that now has to have every one of those has to go back to the ZIO runtime. And I think a really powerful example of this was this operator called toPull. So when we implemented channels and we went to ZIO 2.0, we implemented this toPull operator as kind of a backwards compatibility thing. We had some of these lower level operators where we needed to be able to work with them in this way of, well, I want to take one here, and I want to take one here, and I want to take one here. And so what this operator let you do is take this channel representation and essentially bring it back to this effectual iterator representation, right? So if you look at this toPull, it's the same signature that we looked at before. And so in a way, this is a really nice operator of, it's very intuitive to work with when we need to do low-level things. It solves our problem. It's something we want to use. But it's actually an operator that undermines all of those optimizations we talked about. Every time I do toPull, I have to go through a whole bunch of different ZIO effects here. I mean, we can see there are 2 levels of nested ZIO effects here. And so I'm undermining a lot of those optimizations that we want to do. And I think, in fact, despite our efforts to kind of get rid of the uses of toPull, it still appears in a good number of places internally within the stream implementation. And so chunking continues to have a significant impact on performance. Let's see. Okay. Maybe going over here. Okay. That's strange. Let's see. There we go. The other disadvantage that we saw with moving to channels is that if you didn't use this toPull, it, I think, actually became more challenging sometimes to implement custom channel operators because, again, one of the advantages of the earlier encodings was a stream was just this ZIO workflow. And so you could look inside it, you could do whatever you wanted to with it. Versus in this new world of channels, the channel was a little bit opaque. You you could ask the channel executor to run a channel and run the whole thing, but if you said, well, I just want to get one element to it, or I just want to feed one element to it, you had to work around things a little bit. You had to use this to poll, or if you wanted to just feed a single element, you had to like create a queue, and you had to like wire the queue into the channel, and then you had to offer to the queue. So it was a little bit awkward that way. Okay, so that's where we've been. How do we take all that and go forward? And so what I want us to think about is this idea of streams as being fundamental. So if we think about all these other representations, they have at some level been built on the idea that we have, you could think of it as 2 layers of architecture, right? We have our base layer being Zio, or whatever effect system you want to think about. And then you have streams being built on top of that layer, right? The Zio is the first floor of the house, Z-stream is the second floor of the house, and is built on top of and implemented in terms of this lower level of the house. But I want us to think about, what if that's actually not the right way to think about it? What if the right way to think about it is streams themselves, they are the first level. And if anything, maybe Zio and streams are both at the first level, or maybe actually streams are on the first level and Zio is on top of streams. So let's think a little bit about what that looks like and what that would mean. So to start that process, let's go back to this idea of this channel data type, which definitely seems a little bit scary with these different type parameters. But let's focus on the output types. So we got the environment type, which is like the Zio environment type. We know what that is. And then we've got this out error, out elem, and out done types. And so what you can think about these different types as is generalizing over both what we could call normal computations, the Zio computations that we looked at the very beginning, and streaming computations. And specifically, what we can see here is that this out elem type, that corresponds to the data type in a stream. The contract of a Z channel is that it's going to produce 0 or more out elem elements, and potentially infinitely many of them. And then at the end, if it finishes it all, it's going to finish with exactly 1 either out error or out done value. And so if we think about that, then we can say a channel generalizes the idea of computations that produce incremental results and computations that produce exactly 1 result. And so here's what that would look like. If we wanted to, we could say a Zio, right, our Zio REA that we're familiar with, that we started this talk with, is just a channel where the environment type is R, where it doesn't need any inputs, right? Other than the R, it doesn't read anything else. It's just ready to go with what it's got. And it's never going to produce any type of incremental output. That's why we have nothing for that out element type. And it's either going to fail with an error of type E or succeed with a value of type A. So if we're being provocative here, we could say that a Zio workflow is just a special case of a channel that doesn't produce any incremental results. And so in principle, we don't need to build streams on top of effect systems at all. If we were able to just build an implementation of this channel thing, we would essentially get Zio for free, right? If we could implement this channel and we could implement a way to execute a channel, we could, if we really wanted to kind of go the most extreme direction, we could make Zio this type alias, and we would get all the operators on Zio. We may not want to go all the way there. We'll talk about that a little bit further, but let's push the envelope while we can. And so let's think more about what this would look like. What would it take to have a channel be the primitive? And the answer is it would look a lot like Zio. So we take Zio itself. I mean, I think a lot of times we just kind of take it for granted of like, OK, we have Zio and we build this stuff on top of it. But Zio isn't magic, right? It was implemented by people in this room. And the basic way that Zio works is Zio's got a bunch of subtypes of it, probably 10 to 20. And really the way you run a Zio in Zio 2.0 is really you have this one fundamental method that here I've called unsafe fork. But in the Zio context, it would take the Zio and it actually creates one fiber that is actually running, that is unsafely forked and is going right now and is just interpreting that structure of that Zio and looking at each of those cases and processing one of them and then processing the next and then processing the one after that. And that's what it is. That's kind of what you need to make Zio work. And so you could say, well, OK, if we can do that for Zio, why can't we do that for Z-channel? And in fact, I don't think there's any reason we can't. We can imagine being able to run a channel to produce a channel fiber that represents the running computation of that channel. So just like we have a Zio, you fork a Zio, you get a fiber. You have a channel, you fork a channel, you get a channel fiber, which the channel itself is a description of this computation, just like a Zio is. The channel fiber is that running computation that you could interrupt, or you could wait for the value of, or we'll see you can do other things with, because this channel has additional structure. And really, all we need to do to make this work is we need to be able to implement this channel fiber in a way that handles the additional cases of this Z-channel data type. Right? So to implement a Zio fiber, we need to take all those 10 to 20 cases of the Zio data type, and we need to interpret them in a way that is faithful and has the correct semantics. And if we want to execute a channel fiber, we need to take those cases of a channel and we need to interpret them, again, in a way that has the correct semantics. So let's dive a level deeper here. Let's look at what are the cases. And one of the things that becomes apparent pretty quickly is a lot of the cases are actually very similar, which makes sense because we said that a channel is essentially a richer version of Zio. It's a version of Zio that has all the structure of Zio and then some structure on top of that. So let's look at some of the ones that are the same. So one of the most basic constructors for Zio, as well as a channel, is succeed, which we could think of as introducing a success type, right? I can produce a Zio that just is done with the value 42. And I can produce a channel that just terminates with the value 42. Similarly, we have fail, right? We can create a Zio that fails with a certain error message. And I can create a channel that fails with a certain error message. So both of these you could think of as fundamental operators for one of those type parameters. And of the 7 type parameters of channel, 3 of them are the same ones as in Zio. So we're going to have a lot of the same operators that correspond to each of those type parameters. Fold. So fold is the operator that lets us compose one workflow with another. Right? We have one workflow that finishes with an error or success value. We get to go on and do another workflow based on that error and success value. Again, we have that on Zio, right? And we can implement flat map and fold in terms of that. We have that on channels. What we could call the environment constructor. This is the one that lets us access the environment. Again, we have an environment parameter in both Zio and Z-channel, so it makes sense that we should have a similar constructor that lets us introduce that type parameter. Provide. Provide is the inverse of that. Environment lets us introduce an environmental requirement. Provide lets us satisfy the requirement. Ensuring. There's slightly different implementation between Zio 1 and Zio 2 for some of these operators of like whether they are really primitive or really implemented in terms of other operators. But both of these data types have a concept of resource safety. and then some concept of merge or race. Both of these data types have some concept of concurrently executing two workflows. In the case of ZIO, we call it race. In the case of Z-channel, we call it merge. So all of these operators, very similar, right? We essentially have a implementation of all of these operators. In some cases, they may be more complex because they also need to take into account some of this additional structure. But all of these operators we essentially have on both data types. Let's look at some that are different. So one is what we would call emit. So if we go back to the Z channel and we said it has this error type, this done type, and this element type, emit is what lets us introduce the element type. So it's exactly like succeed, except this is going to write one value to that output channel instead of succeed with that value in that done channel. Read. So read is going to be the fundamental operator to introduce those three input types. One of the other differences between a ZIO and a channel is that a channel can take these inputs. It can take an input error, an input element, or an input done. And so what this read constructor is going to do is say, well, I want to read some input. And it's going to have a way to handle the case where it's upstream gives it an error, an element, or a done value. Pipe to. So this you could think of as arrow composition if we're more category theoretic, or essentially just composition of the input and output types. Of if I've got one channel that outputs A values and another channel that takes A values as input and outputs B values, I should be able to put those together like a pipe. And finally, there's a constructor called concatall, which we could think of as the version of flat map a little bit for that element channel. Of if I have a channel that emits a bunch of elements, I should be able to take each of those elements and construct a new channel, and I should be able to put all those channels together and collapse that whole thing back down. And that's really it. Now, again, there's complexity in the implementation here of we've got to keep track of these different things. There's more that we need to keep track of here versus when we're just working in the world of ZIO, because we need to keep track of who our upstream is and who our downstream is and how that's changing as we're executing one of these channels. But as we look at this, there aren't actually that many additional cases that we need to handle to implement this channel fiber runtime from scratch without relying on ZIO. And so then just like we looked at the additional cases of channel versus ZIO, we can look at what a channel fiber would look like versus a ZIO fiber. So a ZIO fiber is defined in terms of these two fundamental operators of wait for the result of the fiber, right? It's going to give you this exit value that's going to say, okay, the fiber is done, and either it succeeded or it failed, and here's the result of it. And interrupt, which is going to attempt to interrupt the fiber, and is going to then, after interruption completes, give you the result of interruption. And this fiber ended up being quite important in ZIO because it was the basis for all these concurrent operators. And we could think of as in the ZIO world, this was the solution to the problem of all these kind of ad hoc things we wanted to do. Of like, okay, if I want to do very orderly things, I would do zip par, or I would do race. We had these operators. But if I wanted to do these bespoke things that didn't quite fit in those patterns, I would fork fibers myself, and I would use them to do whatever I wanted to do. And so if we want to support the same thing in this world of channels and streams, we want to solve this problem of these bespoke operators that we want to have in a principled way, what we really need is this concept of a channel fiber. And we need to think about what operators it needs to support. So again, just like the channel has more type parameters you can shake a stick at, the channel fiber has a whole bunch of type parameters. Just like the ZIO fiber, you lose the environment parameter because by the time you've created a fiber, you're already running, so you already have your environment. The channel fiber no longer requires an environment, but it has those other type parameters. And so the first things you can do with a channel fiber is you can await it or interrupt it. And you'll see that you get essentially the same thing that you do with a ZIO fiber. You're eventually going to get an exit value that tells you this fiber completed with this done value or this error. And in fact, if we took that definition of a ZIO as just a Z channel with those 3 type parameters substituted in, this definition of a channel fiber would be identical to the definition of a ZIO fiber, which tells us that we're on the right track here, right? That like when we do that substitution, we should get back to the same thing. So these are the operators on a channel fiber that are analogous to the operations on a ZIO fiber. But we've got all these other type parameters. So we've got this additional structure. So we're going to need some additional operators that reflect that structure. And so the first one is we have to have some way to work with this out element type. Right? So far, the out element type appears in the channel fiber, but it doesn't appear anywhere in any operator we can actually call on the channel fiber. So the channel fiber supports a method called read, which just says, I'm interested in reading one value from this channel fiber. And it's either going to return the next element if this channel fiber is still running when it has an additional element, or if this channel fiber is already done when you try to read from it, or becomes done before it emits any other element, then it's either going to give you that error, or it's going to give you the done value that that channel fiber completed with. And so you can think about this as the, in a way, more principled version of that poll thing we were looking at before. Right? I mean, we have a slightly different signature here, but we have the same possibilities when we pull. When we pull, we're either going to get another element, or we're going to get an error, or we're going to get a message that says we're done. And we may get a done value that may be significant, may not be significant. So this is giving us this ability to do that very custom pulling that we want to do. And now we actually have a data type that supports that for us. The other fundamental operator that we're going to have on a channel fiber is the ability to write to it. And so here we can write an error to it, we can write an element to it, or we can write a done value to it. And this, again, lets us do something with those 3 input types. And we can also think about this as the more principled way of doing push. So again, in streams right now, if you have something like a sync, and you want to manually push some values to it, it's a little bit awkward to do it. You've got to create a queue, and you've got to connect the queue to the channel, and then you've got to offer values to the queue, versus this gives you that interface you want to at that lower level to say, well, hey, I just want to push one value right now, and then maybe I want to do something else, and then maybe I want to push another value. So we've got these 2 sides of this channel fiber represents this running channel, and we can push and pull values from it. All right, so that was us pushing the envelope. And I think hopefully you see from this how we could, if we wanted to, go and implement channels like completely without ZIO. And in the extreme case, we could just say, well, ZIO is a type alias for a channel. OK, now, great. Where are we actually going from here? So I think ZIO is probably not becoming a type alias for Z channel anytime soon. I think it's a very helpful thought experiment, but we can see that there's some complexity in representing a channel versus a ZIO because of all these additional things. If you have an upstream and a downstream, and we need to keep track of these things. So I think both for just not screwing anything up with ZIO, as well as making that as performant as it could possibly be, ZIO is going to continue to be ZIO and is going to be very optimized for that case of not having these intermediate outputs. But we can still focus on making channels their own fundamental data type in the way we've been talking about here. And all we really have to do for this is we have to add one more case to that list of channel constructors that we talked about. And it's just going to be one that's called from ZIO. And it's going to let you take any ZIO workflow, now that ZIO really is going to be its own thing, and run it as part of a channel. And one of the things to notice here is there are tremendous optimization opportunities from this that you can actually only take advantage of because of Zio, that you could not do if you had a generic F. And the reason for that is if we're going through in this channel fiber runtime and we see we've got a from Zio, Zio, well, if it's a Zio, we can actually look at that Zio and we can see what case it is. So if you've done something like you've tapped your stream and you've just said like, hey, Zio.succeed, print line this thing, or Zio.succeed, log this thing, well, we could say that this is just a Zio succeed. And we don't need to fork an additional Zio fiber to do that. We don't necessarily need to call the Zio runtime to do that because we're already a fiber. We already have all the stuff that a Zio fiber has. We have the fiber refs. We have our own run loop. We're doing all that stuff. So if we want to, we can just execute that ourselves. Versus if you were working with just a generic F type, what can you do with it? You can only use the operators that that exposes, which is basically you can unsafe run it, which is going to do all that stuff of spinning up whatever infrastructure is associated with that runtime. So there's a lot of, I think, interesting stuff that we can potentially do with that. OK, so where are we with that vision? So we've implemented this channel fiber runtime. We're in the process of hardening the implementation, optimizing it. We have much more to talk about with this at Zio World next year. But we've already got essentially all of the test suites for channels passing with this channel fiber runtime implementation. One of the things I do want to emphasize for everyone here, and I mean, I think a lot of credit goes to John for this, is that this wouldn't have been possible without the next generation runtime introduced in Zio 2.0. There is significant additional complexity in this. So we've got to keep track of these upstreams and downstreams and how we're moving between them and all this stuff. And in the Zio 1.0 world, or really the kind of final version of Zio 2.0 world, there was so much other stuff going on in the runtime and so many other concurrency issues we had to keep track of that I don't think it would have been manageable to add this additional complexity to this run loop and kind of implement this whole thing at the space level. But the structure that we have for the fiber runtime in Zio 2.0 is so clean, where we just have these fiber messages come in, but then the entire run loop is synchronous, that it makes it possible for us to implement this. So that's where we're looking to go. I think things I would encourage you all think about is this idea that we shouldn't think of streams as being this higher level that's built on top of effect systems. Instead, we should think about streams or channels as being fundamental. And effect systems as actually being specialized versions of these for the case where there's no incremental output. And it may make all the sense in the world to have a specialized version for that because it lets you simplify things, because it lets you be more optimized. But if we're thinking conceptually, our mental model shouldn't be one level of the house is effect systems, the second story is streams built on top of that, but really they're the same thing. They're all the first level, and maybe it makes sense to kind of have two houses just so one of them can be really specialized for what it's doing. And really all of this is in service of achieving the lowest possible overhead for these stream operations, because as we talked about at the beginning, streams are something that are very, very important, and important not just for kind of arbitrary reasons, but for reasons that reflect something about the nature of the world and the way the world works. And we want to be as efficient as we can be with this so that you can actually take advantage of streams and take advantage of this richness and composability without getting to a point where you say, hey, there's too much overhead here. We gotta not use this. We got to use something else. So that's where we're going here. Again, I think this would be definitely impossible to do with generic effect types because you don't have the ability to introspect them in the same way. And so I think it's a really nice example of kind of what you get with Zio. And it would have been impossible to do without the runtime work that has occurred this year. All right, that's a lot from me, and I am keeping everyone from dinner and celebration here. So I just want to wrap up and thank all of you. First, thank John, Sandra, all of my colleagues at Zyverge. I think you've had a chance to hear from a bunch of them early today. You're going to hear from more tomorrow. I'm really privileged to work with some incredible colleagues. So I want to thank all of you for being part of this journey, and it's definitely made things very, very, very rewarding, very special for me. Also, all of the Zio contributors. So there's some overlap between those two categories, but for people who are Zio contributors and are not my colleagues at Zyverge, it's also been a real pleasure with you, and I think you all continue to do amazing things and to both push the envelope and push me. Zio users also pushing us in a very good way and putting your trust in us, which is something that I take very seriously, and I want to live up to that trust. And then everyone else who helped organize this conference. There are a bunch of folks here, Agata, who've been doing, working really hard to make this event possible and make it an awesome experience for all of you. And then just all of you for taking the time to attend today. I know some of you traveled from, some people from Asia, from really the opposite side of the world. And those of you who are just taking time out of your day to listen remotely and kind of got a ticket and took the time to do this. Hope you found this to be a rewarding day, and hope you're excited to come back tomorrow and hear more awesome stuff. Thank you so much.